Hi, my name is Rebecca Freese and I'm a student at Augsburg College in Minneapolis, Minnesota. This summer I participated in an REU at South Dakota State University, and this is weighing motion-based live load fragility analysis for a steel bridge using a structural health monitoring system. The objectives for my project were to model the probability that a bridge is damaged as 5-axle trucks cross over it, and then to determine which truck characteristics cause the most significant strain on the bridge. Field data for this study was collected at an existing bridge in Iowa. WIM data composed of class, number of axles, speed, axle weight, and axle spacings were collected for trucks crossing over the bridge. And then strain time history data was collected from sensors placed on the bridge that recorded global bridge response as these trucks crossed over. So here we have a side view and a bottom view of the bridge, as long as the configuration of a 5-axle truck with the characteristics we were looking at marked. All of this data was used to create a best fit regression model to calculate load ratings, which can be seen at the bottom of this slide. So fragility curves were generated by inputting the WIM data into the best fit regression model to calculate different load ratings. A load rating less than 1.3 was considered a failure, and then the number of failures was turned into a probability of failure. This is the probability of failure is plotted on the y-axis with the x1, for example, plotted on the x-axis in the lower left corner. This graph didn't really make sense from a civil engineering point of view because we expected that as the x1 got bigger, the probability of failure would also increase. So using Bayes' theorem, we could convert this probability into a cumulative weighted probability of failure, which is seen at the bottom right corner. So these graphs are what we call the fragility curve, and they were generated for all of the axle weights as seen here. They all have similar shape, they increase rapidly and then reach a probability of 1.0 and stay there. Here are the fragility curves generated for the 4-axle spacings. These look different than the axle weights, which is understandable, and then the most different looking curve is for x6 in the bottom left corner, which looks linear. This could be due to because x6 is the largest spacing on the truck. As the truck gets longer, it can't necessarily get heavier because it still has to abide by weight limits for the roads, so this makes it more of a linear relationship. Here are the fragility curves, all on the same graphs for the axle weights and axle spacings, just so we can compare them better, see the different ranges of the values, and things like that. So after we created our fragility curves, we wanted to determine which variables most significantly affected their fragility curves. And we did this by seeing which ones reached a 1.0 probability value first. So a Kruskal-Wallis test was done on all of the weights and then on all of the spacings separately. And the results of the Kruskal-Wallis test told us that there was at least one variable in each of those groups that was different from the others. To see this information graphically, we did quantile plots. So here's the fragility curves for x3 and x5, and you can see that they do look different. x3 looks more steep than x5. So the quantile plot for this on the right shows x3 on the x-axis and x5 on the y-axis. And the plot lies entirely below the reference line, which means that x3 is more significant, or it reaches the 1.0 probability value first. You can compare this to the fragility curves for x7 and x9, which look very similar, and then the quantile plot lies almost entirely on the reference line. This information let us deduce an order of significance, with x3 and x1 being the most significant axle weights, and x4 and x8 being the most significant axle spacings. Then, to control the error rate that could have been in the first test, we did post hoc non-parametric pairwise U-tests and a Wilcoxon signed rank test. So a W statistic was calculated along with a critical U value, which can be seen below here, the equations for those that were used. And then anywhere where the W statistic was larger than the U value, that pairing was considered significant. So here we have all the possible pairings of axle weights, and the bold ones in the table are marked as significant pairings. So from this we can see that the x1, x5, x1, x7, x1, x9, for example, are all significant pairings, We can compare this and create a new order of significance, which can be seen at the bottom of the screen. Here, the underlined values, x1 and x3, are where they differed from the first order of significance. And then the same thing for the axle spacings, x6 and x8 were switched in the first order of significance. But if you look in the table and at the Kruskal-Wallis tests, you'll see that the x1, x3 spacing, or the x1, x3 pairing was not significant. So it really doesn't matter which one comes first. Same thing happened with the x6, x8 spacings. So this is our order of significance: x1, x3, x7, x9, x5 for the axle weights, and then x4, x6, x8, and x2 for the axle spacings. This information should be kept in mind when restricting 5-axle trucks from bridges to preserve the integrity of the bridge. If you have any questions or comments, let me know. Future work is being done to see how the bridge stands up over time, and I'd like to thank the National Science Foundation for funding this and the rest of the people on this list. Thank you.